Well then, my name is Peter Tuma. I'm from Charles University in Prague, and I want to talk a little bit about the work my colleagues and I are doing on
Could you
tracking
please
the performance of
increase your
Graal.
volume, Peter?
Um, I'll try to speak a little bit louder. I think this is auto-configured
Okay,
by the
that's
Zoom client. So is this better?
yes, thank you.
Great. Okay. So I'm from academia, but I'll really start with a little bit unusual set of disclaimers. So I'll be showing some performance data, and I'm not going to read this all, but I really want you to remember that I'm showing data from development versions of Graal, so and of patched versions of benchmark. So if you need real data, you need to measure them yourselves on stable things. These are collected from unstable versions. So please keep that in mind. So anyway, um, what is our performance testing goal? We really want to make performance testing roughly the same as is standard functional regression testing. So we assume people would just commit their modifications of Graal to a pipeline. And alongside the standard regression tests, we would run the performance tests and also send back some notifications to the developer when a particular commit breaks performance. So we did write a small dashboard that does roughly that. You see a screenshot here. We have an overall trend where we just track all the benchmarks together. Then we have a list of recent individual performance changes that we've detected, and we can just click on the individual changes and we see things such as the specific history of performance for that particular benchmark and the individual measurements and so on. Now, with all this, we can do sort of high-level graphs. I will show you one later. Uh, I'm not going to talk about the internals of the dashboard, though, except for very few data points. So we are benchmarking both C and E version of Graal on GDK 8 and 11. We don't measure all the commits, but we measure the top-level merge commits. So we get about 6,000 versions to be measured per year. We use many of the well-known benchmarks, so Scala Bench, which includes the Da Capo benchmark, Spec JVM 2008, however, in a modified version, so it has nothing to do with spec scores. We use the Renaissance suite plus some internal micro benchmarks, so around 130 workloads in all. And we run our measurements on a dedicated set of servers, around 40, give or take. So it's not yet in a shape where one could run this on a local development machine. It needs a smallish cluster of measurement machines. So I promised some overview graphs. Here's one. It really puts an average performance across all the workloads we have into one plot. Um, just to show you the very nice good news that the Graal developers are really doing a good job if this is the metric, and performance appears to gradually improve most of the time. Obviously, this kind of aggregate graph is just to make you feel good because all benchmarks in it have the same weight. So really, it doesn't tell you anything about the performance for your own application. It's just something to open my talk with. So if we want to look at individual benchmarks, obviously the problem is how to detect changes. Here is one plot where the x-axis is time, so it's mostly versions, but also individual measurements. Each data point is a single number from a benchmark. The colors show moments where we restart the benchmark, so we measure each version multiple times, obviously. And a mathematician would tell you that this is simply a time series change point detection problem, but with a few twists. So in particular, we don't have just the time, we collect hardware performance counters. So we have things such as the amount of cache misses triggered by benchmark execution, the instruction counts, and so on. We can add more data points to any version if required. So we don't really measure on commit, we measure on demand whenever the time series analysis needs more data to decide whether there is a change or not. The data points themselves are not flat structure. They are hierarchical because we restart the benchmarks. So we have sets of data points from individual runs. What's a bit more troublesome is we are really more interested in changes near the end of the series, right? Nobody worries about regressions that appeared a year ago, so we really need to react quickly to any changes that are near the end of the data set, and that is in fact a different problem than just analyzing the whole time series. And we cannot make more strong assumptions about the data distribution because the performance of the benchmarks is mostly just weird mix of everything. So in the end, we don't really do a whole time series change point detection. We do a subset of it where we use certain bootstrap confidence intervals of mean differences to decide. There's a link in case you're interested in the formulas, but I would want to talk more about the results we have. And the first one is what share of versions do we see changing in Graal? So in this table, you see three numerical columns. The first one tells you out of all versions that we see, what is the share of versions where that benchmark has changed. And you see that most benchmarks do exhibit changes. So that means the benchmarks are sensitive to the Graal development um, at a rate of 1 to 5-ish%. So if I take into account the speed with which we consume versions, this means that if you have 10 to 20 commits per day, you would see a single change per 1 or 2 weeks. The next column is perhaps more interesting because what we did is we took a few hundred, about 600 or 700 of changes that we detected automatically, and we tried to decide manually whether the changes are really there or not, because we need to know whether the formulas work without false alarms. And based on the amount of green you see, I would say that the detection is mostly reliable enough, so we mostly don't have to care, except for some benchmarks, especially micro benchmarks, where the detection rate is slower. And that's especially because we see the benchmarks exhibit some invalid behavior, or somehow the measurements are invalid in that even though the performance data really does show some change, that change cannot be attributed to code. So that's not something that we want to report to the developers anyway. Also, in some cases, it's very difficult to manually classify a change, because if we have a benchmark which has something like 10% variability and we see 1% change, a human essentially isn't able to say whether the change is there or not. So that's a bit of an issue in the manual classification here, and therefore it's not entirely randomized, but it's just a side issue. So that's one look at the benchmarks. The other question we might want to ask ourselves is, do we have too many benchmarks or too few perhaps? So this is a graph where we see how many benchmarks change together in a particular commit. So we see that if we take commits where some benchmark has changed, in more than 60% of the cases, it was just that single benchmark and no other benchmark. So majority of changes really are limited to single benchmarks. For me, that's a bit of an indication of the fact that we don't really have too many benchmarks. We have perhaps too few, because um, I would expect more benchmarks to react together. There's also the question of whether the benchmarks somehow overlap in functionality. So this is a sort of an attempt to squeeze this information into a single screen. So in this table, each row and column uh, stands for one benchmark workload, and the size of the dot you see tells how many times out of all changes we saw, how many times the two benchmarks selected by the row and the column changed together. So a large dot like the ones in the middle mean that those benchmarks always change together. And um, from just eyeballing the table, my impression is that there are really only few benchmarks that really often change with another. That's a sort of a row of fat dots that you would see. Also, you might notice that there's sort of a whitish part in the middle. That's because the Renaissance suite or at least the version we use now, has not been around for so many years as the other ones, and therefore we don't have so much data out of that. So if I just slow down a little bit and summarize some takeaway, um, the first thing we perceive is we probably do not have enough benchmarks because overlap in performance changes is relatively rare, and that is coupled together with one issue which I think is really huge, which is it's not really clear how to define coverage. So for normal regression tests, people would worry about coverage, but for benchmarks, that problem is still open because it really depends a lot on what the final application the benchmark is supposed to represent, and so on. Also, it feels that, at least in our case, the reliability of change detection per se is not that much of an issue, but it requires a reasonable measurement procedure. We cannot just take benchmarks and run them ad hoc. We have to pay attention to what we are doing. And also, especially the micro benchmarks may require very special handling. Uh, Speaking of measurement procedures, if you've seen JIT performance, you already know that a single benchmark run doesn't really tell the whole story. So we might run the benchmark once and we see nice compact distribution of results coming from that single run. However, because the JIT is non-deterministic and many other things in the system are as well, if we run the benchmark multiple times, we might see more runs which really have significant variability depending on the benchmark. So the next table I want to show you is if we decide on the required accuracy, for example, 1%, how many runs do we need for each benchmark? And the table has different columns for different versions of Graal, so Community and Enterprise Edition on JDK 8 and 11. And my biggest takeaway from this one is it's very, very bad, right? Because for roughly half of the benchmarks, we would need more than 100 runs. And we have to remember that a run involves warm up, etc. So it really might take several minutes. So running that many benchmarks over hundreds of minutes or more is not really very scalable. Another fact is it's not just the benchmark, it's the combination of the benchmark and the platform that determines how many runs are needed. So you can see that sometimes JDK 8 seems to be more stable than JDK 11, sometimes it's the other way around, etc., etc. So this table looks bad, but maybe perhaps asking for 1% accuracy is too much. So this is the same table, except we are now looking at the number of runs needed for 5% error, 5% accuracy. And we see that suddenly the table is mostly white. There are a few red rows where 5% is still difficult. And the reason why the accuracy, the table changed so much is that the accuracy roughly follows 1 over square root of n with the number of runs. So essentially, we wanted 5 times smaller accuracy, so we need 25 times fewer runs, and that's a lot. So again, if I want to summarize into a few takeaway points, then first of all, obviously running the benchmarks only once may not be enough in many cases, even though in some situations you saw that one run is perfectly fine. The issue is with non-deterministic compilation, which is visible, especially with micro benchmarks, which tend to amplify certain weird behavior. But also in the presented tables, we saw simple cases of high variance. So I didn't deal with issues such as multi-threading into benchmarks. If the benchmarks are heavily multi-threaded, they usually need longer execution time to get more stable results. Aiming for excessive accuracy backfires quickly. So one shouldn't hope to squeeze arbitrary accuracy out of benchmarks. One should really take a look at the benchmark and decide what accuracy that particular benchmark is capable of. We are not yet sure how often the relevant parameters here tend to change. So whether every new version of a compiler can exhibit different stability than the predecessors. That's something that we want to look at later, but I don't have data right now. Now, I've also mentioned that we run and collect different metrics, so not just wall clock time, but also, for example, thread clock time or instruction count. So this other table is again a table telling us how many runs we need to measure something accurately enough. But this time around, the columns are for different metrics. So here you can see that for most rows, some of the metrics are much more stable than the others. And if we combine the result from all of them together, we can again detect some changes with more reliability with fewer runs. Essentially, this is a trade-off. Either we dedicate more time to measuring or we reduce the accuracy with which we report the changes. Now, there's another issue, which is what if we have benchmarks where we see a change in instruction count, for example, but we don't have enough runs to confirm that change on wall clock time? Should we already report it or should we execute more measurements? There's a graph which tries to answer this again. So in this plot, every dot is a case of performance change. So every dot represents a situation where we had two versions, performance changing from one to the other. And we plot on x-axis, we plot the change in wall clock time. On y-axis, we plot the change in instruction count, which is a nice and stable metric. So we see that in many cases, the two metrics are really in sync, and we see that whenever the wall clock time changes, the instruction count changes accordingly. However, there are cases where we see benchmark easily exhibiting 2x change in performance, but no change in the instruction count, in the count of instructions executed, or the other way around. We also see situations where we see instruction count change wildly, but the performance staying the same. So that leads us to an observation that maybe the wall clock time should be understood as a sort of a main metric, because that's what people care are about, performance, right? Or we could pick some other metric like energy consumed per iteration. We also tried that. And we should consider the other metrics as secondary. Unfortunately, that's not all there is to it, because even the wall clock time itself is not as portable and stable as we would like it to have. So here, what we did is another plot where, again, each dot is a single case of changing performance. And we just took a set of situations where we had Graal builds changing performance, and we measured the same versions on a different machine on the Amazon cloud. And the dots show how the two platforms, our hardware versus the Amazon hardware, perceived the change. So we see that we have cases where we see large change locally, like 30%, and that change is almost not visible in the cloud. And we also see changes where what is an improvement, for example, on our platform is in fact a slowdown or a regression on a different hardware platform. So that again complicates things a little bit in the reporting phase, because what we see may not be a universal observation. And obviously trying to measure each change on many, many hardware platforms again is too expensive. So that's a bit of a problem. By the way, this plot doesn't show variance, so I don't like it so much, but it is somehow informative. So to summarize here, um, in our experience, looking at more execution metrics can improve accuracy. However, we have to be careful. Sometimes it can help in the investigation when we, for example, see that the amount of cache misses changed. That gives us some more data to work with. And again, this gets me back to the issue of aggregating results. It's not really clear how to combine possibly conflicting results, such as when we see some metric changing and the other not, or some benchmark improving and the other regressing. So that's still an open issue where the user feedback, again, I believe is very important. Now, I've been showing measurements, but I haven't been presenting any changes, so I just picked two tiny examples. One is a micro benchmark that just tries to find the first negative array item. So you see the code fragment here. And in this particular benchmark, in one scenario, we saw very clear repetition time change between 230 milliseconds per repetition and 170 milliseconds per repetition. So quite a big jump in performance, but that jump was only visible on walk log time. The instruction count didn't change. The cache misses didn't change. So most of the other counters didn't change. And what also attracted our attention is we saw the benchmark fluctuate between the two uh, scores across multiple versions across several days. And some of those versions had changes that were clearly absolutely unrelated to what the benchmark does. So that was strange. So after looking at what's happening, we saw that in fact, the compiler does a very nice job of inlining and expanding everything in the benchmark. So the kernel of the benchmark, in fact, uh, compiles in its entirety into like 9 CPU instructions on x86 platform. So I think a human writing the loop would probably remove one extra loop count test, but that would be it. And what's also remarkable was that this loop executes at an extreme efficiency. So the instruction per clock count for this loop was 6 when it was running fast, which is quite unusual. The metric is normally around 2 for other benchmarks, or even less than 2. And the way the benchmark was repeated over and over again meant that the actual performance difference between the fast and the slow version on those 9 instructions was just half CPU clock. So in other words, every other iteration of the loop, the CPU spent one more clock cycle executing it. And in the end, we traced the result, the reason for this into the way the CPU schedules micro-ops into the execution ports. So it seems that the CPU is willing to use two different scheduling patterns for this block of code. And depending on what other code precedes this block, one of those two scheduling patterns is used, and one of them is this half cycle faster than the other. So that's something that is interesting to listen to maybe, but it's not something we can ask developers to fix because there's nothing to fix. The generated code is the same with both versions of the benchmark. For another example, which is also a little bit troublesome in terms of what the developer can do, is another micro benchmark which filters odd elements in an integer array. And what we saw here was the benchmark flipping between roughly 5 and 5.5 seconds per iteration. So when we run the benchmark, the times within each run were stable, but whenever we restarted the benchmark, we saw maybe a different time. Again, to a compiler person, this immediately rings a bell as non-deterministic inlining, right? So that's exactly what happened. And since we report average performance, we saw situations where one of the two scenarios uh, was represented more or less often in the total mix. So we saw, for example, situations where the performance changed by 10 or 20%, but it was not because each single iteration would be 10 or 20% faster or slower. It was because in the mix of all runs, the share of faster runs or the share of slower runs changed. And again, that's something that's difficult to report and explain. In this particular case, the reason was the inliner using a cache of previous code sizes from previous compilations to decide on whether to inline or not. And depending on how various compilation jobs raced against each other, this cache was either populated or not, and that influenced the inlining decision. On this point, I would observe that um, if we look at how the benchmark is structured, it's a single large loop which calls a lot of nested functions. And in this setup, the invocation counts on all those nested functions change together, and therefore they reach the thresholds for compilation together. So this benchmark design actually seems to increase the likelihood of firing multiple compilation jobs at the same moment, and that increases the likelihood of the inlier flipping in the way I described. So these are just some observations about the cases we saw. My takeaway from this would be the reasons for a performance change aren't really always directly connected to committed code. So especially in micro benchmarks, they may exhibit quite fragile performance. And it's not really always the case that the author of the commit that led to performance change would be the person that should be fixing the change. Sometimes the commit just reveals a different set of things that happen inside a compiler. Also, it's quite hard to tell whether performance regressions should be addressed, especially with micro benchmarks, because they don't really represent application performance. So one can always say, yeah, the micro benchmark regressed, but this is not something that would happen in a real application. So maybe we should always have sets of real workloads and sets of micro benchmarks. Micro benchmarks are good because they help highlight very specific issues, but the overall application benchmarks tell us which issues really matter. Also, the effort needed to investigate the reasons for performance change is not very predictable, and I've seen today a lot of other people talking about how they investigate performance. So I think there's a lot of inspiration in that. So anyway, my time is almost up, so thank you for your attention. Um, 4 data points I want to leave with. One is we should not really treat all benchmarks the same. So situations where people just run the benchmarks, collect the scores, and treat them in a similar way, these are not a good idea. We really need to distinguish per benchmark and platform which is running the benchmark. Micro benchmarks are, I think, absolutely needed, but they should really get a special treatment. They shouldn't be mixed together with bigger benchmarks. And also, I think the evaluation cannot really stay with the developers only. The developer can say when a functional test fails, that's easy. But the developer cannot really say whether a performance change matters in the bigger scheme of things. Not always. Okay, if it's a times 200 slowdown, then it's obviously a big problem. But in general, this is not possible. And on that topic, I would like you to invite to contribute to Renaissance Benchmark Suite, because if you do, then we will start benchmarking your code too. So that's all from me, and thank you for your attention.
Is there any way for us to run these benchmarks associated with a PR? For instance, because running it on our own private platform obviously has its problems. So.
Yeah, so I know what you mean. So what we do is when we have a change, we provide a complete dump of what we did. So you can see the results, you can see the command lines used to execute the machines, and so on. We don't have that yet. I know that, for example, folks from MongoDB, when they do benchmarks, they take care to have a result which can really be reproduced easily. So I think it's just one archive away from doing that in our case. So we can give you the exact executable, send it to launch to get the benchmarks to run. Obviously, what we cannot guarantee is that you will see the same change um, in your setup, but that certainly helps in chasing whatever is happening. Since we use the developer builds of Enterprise Graal, that's where we cannot do that, but for community Graal, that's easy.
We have another question, comment from Nick. Nick, would you like to speak up?
Yeah, so I think you mentioned this right at the start, and I might be misremembering, but so you're essentially running these benchmarks periodically as changes are made upstream. Are you publishing this data online somewhere?
That's what we plan to do. So our aim is we just want to clone the repo for Graal, and you would see that with your commit. So you would with commits that change performance, you would see a link to our dashboard indicating that change has happened. So this should be coming shortly, but it's not yet there. Essentially, because we started by mixing all data together, and we need to separate internal data from the data that applies to the community version.
All right, thank you.
Thank you, Peter. Any other questions for Peter? Okay, in that case, I encourage you all to join the Graal workshop Slack channel for the conference, and we can continue our discussions offline regarding these presentations. I know some of you will be looking at the recordings as opposed to attending them live. So there may be questions. So I request all presenters as well as participants to join the conversation in the Graal workshop channel.